Great. Well, first of all, I wanted to thank Anna for fitting me into the program on very short notice. I wanted to let you know what this project is. Some of you are involved in it. And I wanted to thank the Quantemol team for hosting this event, which I believe is very important. Users and people who generate data to have the occasion to get together. Oh, I need to put my, let's see, down. And I was expecting to talk after Zoran, so I added a view graph in here to give you the context of what we're interested in. I come from the low temperature plasma community, and we are modeling low temperature plasmas often for applications. So we take a very pragmatic approach. Low temperature plasmas are, in general, the electron energy distribution in low temperature plasma is generally non-Maxwellian. Now this complicates life a bit, but we do have a way of dealing with it if we have cross sections for the electron neutral, ground state neutral collision processes. If we have cross sections for all the targets in our plasma, we can go through a Boltzmann equation solver and calculate our electron energy distribution function. The parameter is the reduced field strength. This is E over N. That's the ratio of the external electric field strength to the neutral density. So when we don't have a Maxwellian, we don't have a temperature, we can't define a temperature, but we do have this parameter E over N that suits us very well, us in the plasma community, because people could measure things like ionization rates, mobilities as functions of E over N, and those are the parameters that we use in our models. I'm simplifying a bit. I'm just trying to get to the point quickly. There's an awful lot of details in here. Now, I should say that this procedure, going from cross-sections, solving the Boltzmann equation, getting our transport coefficients, our rate coefficients, this works for any arbitrary gas mixture as long as we have cross-sections for the electron scattering from all the components in that mixture. And I'd like to add, this is important too, that what we need is a complete set of cross-sections, complete in the sense that all the major momentum loss processes, all the major electron energy loss processes are included. So that means that we need elastic momentum transfer, we need total inelastic cross-sections for all the major processes involved, we need ionization and attachment. That's a complete set of cross-sections. Okay? That was my introduction. Now let me say what LXCAT is, which is the topic. LXCAT, for electron scattering, it's an open access website for collecting, displaying, downloading electron scattering cross-sections and swarm parameters. Now I've given you the address. In fact, you could type LXCAT in Google and it's the first thing that appears on there. I'm doing this with my colleague Sergei Pencheshny, who knows how to get Google to put you on the top. Gary and Hagalar, who's been very active in this process as well. The structure of LXCAT is shown right here. We have contributors. Quantemol is one of the contributors. Contributors who set up individual databases. We have the structure that's already defined. And so anybody who wants to contribute data can get their own password. They have their database. They're in charge of managing and taking care of it. And then we have online tools that allow plotting, downloading, comparing, and especially there's that Boltzmann solver on there, online. So that lets us go from the cross-sections to those swarm parameters, electron rate coefficients, transport coefficients that we need for modeling. So then the users can get their data in whatever form they like. I should say at the moment we have 12 different databases, and again, Quantemol is one of those people. 65 different neutral gas species, ground state neutrals. That's mainly what we're interested in because our plasmas are low temperature, the degree of power loading is small, so electrons collide mainly with the ground state neutrals. We're starting to put some experimental databases on there. These are the transport coefficients as functions of E over N. There's been a lot of measurements of that, and we do have some of those now. They're not all public yet because we're still checking. We're doing a lot of benchmarking of codes. We have the one Boltzmann solver on there. We trust it absolutely, but you know, I think people would like to see it compared with other codes, and that is work in progress. We have an ion database, IceCat. This is all about electrons, but the ion component in the plasma is important as well. So there's another database for ions, not quite as advanced, but that's online. And then I wanted to mention, too, to this community that we presented this at the GEC in 2010. And what we're trying to do is make this a community project. This is much larger than one lab. It's much larger than the 12 contributors we have so far, or it could be, and I think it would be useful. So the GEC decided to have a workshop on this topic every year for the next 3. So the workshop in 2011 will be mainly focused on rare gases, and then we're going to more advanced targets for 2012, 2013, and we're open for ideas, we're open for people to work on it. I have given, now it's trying to find other people to contribute as well. There's usage statistics. It is starting to be known. People are starting to use it, and I hope you'll take a look at it too. Thank you. Thank you.
Any questions?
Obviously, because this is the sort of thing that we should discuss about bringing in Family C, and you may already have those
Right,
discussions
yes.
with Leanne.
Yeah.
One of the aspects on that is actually the data verification. We've got 12 databases, we've got 12 different answers.
Right.
And
Yes.
it's the process there. The one that we've used on that is, of course, the KIDA database for reaction rates. Have you seen that one in Valerie Waker, Millie Bordeaux?
No, but that's Maxwellian's,
Yeah,
isn't it?
but
It's
there's-
thermoplasmas.
But the data verification, what they've done is when somebody puts the data in, there's a process by which the data is verified into primary and secondary data for reaction rates, rather than, pick which one you like. I'm
Right.
not sure, not having looked at it.
Yeah.
What's the ensemble? Is everything in it, or is there any recommendation?
That's just the problem we're trying to grapple with right now. For the moment, it's anybody who wants to upload their data can. What we have, and we'll be presenting at the GEC, are the comparisons with experiment and all the available data in that database, which is a way to
We'll
evaluate.
talk over lunch because it's part of the
Yeah,
family
it's
C.
important that we,
You all is
yeah.
exactly that.
But I think we overlap to some extent with your project, but we're very modest in comparison with what you guys are trying to do, because it's very, very limited to these low-temperature plasma applications. Okay.
If you're dealing with cross-section data that's got the resonant structure, is there you have to have some consideration of that structure compared with the energy scale density of non-Maxwellian? So how do you handle this?
Yeah. We've just been talking to Klaus Barchok about that because he's calculated all of his structures in the electron-argon scattering. And yeah, we don't really need, for our purposes, which are again quite modest and quite reduced, okay? We don't really need that kind of resolution. So what he's going to do is take his cross-sections, calculated with a lot of structure, put it through a low-energy analyzer, like if he were doing the experiment.
Averaging over something to scale and
Yeah, yeah.
non-Maxwellian.
Yeah, and then we would use that, and that for our purposes is what we want. Again, our purposes are very narrow, but that's what we would do. Our energy range, I should specify, is up to maybe a kilovolt. That would be ideally what we would have, because these plasmas are often generated with an electric discharge. The total potential across the electrodes might be 300-400 volts a kilovolt. So our energy range is 0 to about a kilovolt, although most of the electrons are much colder than that kilovolt. The averages might be 1 to 10 electron volts. Does that answer your question? Okay.
Since you are using only electron neutral scattering data, I assume it all applies to low degrees of ionization. So
Yes.
what is the upper limit?
You're quite right. You're quite right. When you have a high degree of ionization, you have a Maxwellian. You tend towards a Maxwellian. We're limited here to the cold gas approximation. Everything's in the ground state. I think for GEC 2012, we're going to be looking at the problem of our rotational states are starting to become populated, and so how do we deal with that power deposition and rotational levels. We're looking in that direction, but so far we have not dealt with it. Ideas are welcome because it's a problem. We don't quite know how to do it, but I think for a lot of applications this is sufficient. For many applications it is.